Okay, thanks for joining us for the Western Wheels Conference. A couple quick things before we begin. If you need a certificate, you'll find the link for that here. You'll need to submit a separate request for each session that you attend, and you should receive your certificate in email within 24 hours of submitting the request. If there are any handouts available, you'll find those there. And if you're interested in learning more about any of the products featured in our sessions, that'll take you to the product page for each one. And if you click request pricing, that'll add it to your wish list. Here we are at the wish list. You can either complete the form and submit it right away, or you can keep browsing around and adding items to it to get one big quote. And you can always get back to your wish list right up here in the top right-hand corner. That's it. I hope you enjoy the session. We'll see you on the other side.
Greetings, my name is Darcy Wadle with Electude, and today we're going to be discussing teaching electric vehicle technology. This is often a very difficult topic to introduce to your students because, for one, electric vehicles, it's not something even as instructors that maybe we're super familiar with. Using my own self as an example, I was a technician in the 90s and early 2000s. I started teaching in 1995, and I've never worked on an electric vehicle, but yet back in 2010 or so, I had to teach my first hybrid course to students, and I found that oftentimes I was learning right along with my students. And believe it or not, some of the things that I discovered through that process is, I was maybe making things a little bit too difficult, or maybe some of the strategies that I was employing at the time that I learned through previous years of teaching just weren't working the same way. Well, let me give you an example of that. So let's compare the technologies of a conventional automobile on the left and an electric vehicle on the right. With your conventional vehicle, you've got lots of moving parts, very mechanical. Yet on an electric vehicle, there's very few moving parts, lots of electronics, and it's very abstract. So there's magnetic fields and there's current moving, but very few moving parts, with the exception of the rotor and the electric motor and and your differential and whatnot. But a totally different technology, and therefore I think it takes a little bit different teaching strategy to help students understand it in such a way that they can then feel confident going out there and doing this for a living. And as many of you know, students, if they don't feel like they, confident, they're not going to go out and do this. So it's our job as trainers to break this technology down and to try to make it as simple as possible for our students. So let's reminisce here a little bit. A mechanical engine. Very easy to teach this. You can, I say it's easy to teach, but you can bring this thing into the classroom on an engine stand. You can put a wrench on the front of that crankshaft. You can spin it. Students can see the cam and the crank moving. They can see the pistons moving down. And as you're talking about how this engine works, the four-stroke process, whatnot, you're seeing students moving their heads up and down. They're getting it because they can see it. You can take them into a lab and you can have them tear apart a cylinder head, and you can talk about the valves, and they can see those parts move, and they can understand it through observation. However, if you put an electric inverter in front of a student and you take the lid off of that thing and say, well, see what you can figure out here about this inverter, you're not going to understand how this thing works through just taking it apart and looking at it. There's no moving parts on the inside of this thing. In fact, if you did take the lid off of it, you'd find that it looks like about a half a dozen other things that are electronic. It could be a television set or a microwave oven for all you know. In fact, here are 4 pictures. One of these is an inverter from an electric car. Another is a microwave oven. Another is a stereo, and yet another is a keyboard on electric piano, or electronics on an electric piano. So Panasonic, well, they make batteries, but they also make microwaves. So this is your microwave oven. This here is a stereo amplifier. You might see the 300 volts here and think, maybe this is the inverter, but no, this is your electronic piano. And this here is an inverter on electric car. So yeah, you might recognize some components on those boards and stuff, but largely by taking it apart, are we going to really learn anything about how this thing works? Probably not. Well, maybe a wiring diagram will kind of clear things up. So, years ago we used to open up a wiring diagram for like a blower motor or a cooling fan or power door locks, and it's a relatively simple circuit, with relays and switches, and you can figure out how that circuit works through studying the wiring diagram. I can't even fit the whole wiring diagram on my screen for this inverter. It's just a complicated diagram. Now, obviously, we need to understand how to read this diagram and to be able to do pinpoint tests and so forth. But as far as figuring out how this inverter works, doesn't really do anything for me. And you put this in front of students, and this is just going to intimidate them, and they're going to think, oh my goodness, I'm never going to be able to do this job. So what can we do? What are some strategies as trainers that we can do to break this technology down to make it simpler? Well, years ago, I went to a teaching seminar once, and they were talking about mind maps. And when you begin a training with your students, start with what you know. And I think this is something that I did. It worked for me because sometimes as trainers we just assume students know certain things, or maybe they don't. So I would use these mind map activities to kind of gauge their level of understanding. I would sometimes do these before a lecture, maybe in the middle of a lecture, toward the end, and then it kind of gives you a gauge, in other words, of where you need to go next. So what we're going to do here, obviously this is a recording, and we're not in front. If we were live, this would be probably a lot more entertaining because I could ask you the teachers for some input here, but if you can pretend for a moment that we're in front of a class of students, and I ask them, okay, what are some things you can tell me about an electric motor? It can be anything at all. And so one might say, the electric motor has a stator, so you would put stator on the board here. Another might say rotor. Another might say magnetic fields. And then you say, well, what do you know about an inverter then? Okay, that's good about magnetic, electric motor, but what can you tell me about an inverter? Well, if they're entry level students, they might recall that an inverter is some type of a switching device. Maybe it's DC to AC electricity. But they're not probably gonna, when they're starting out. But hey, we got a starting point here. We know it's some kind of a switching device, DC to AC. It's associated with the electric motor. The two kind of work together. So what we're gonna do now is we're actually going to then from here jump into an electude lesson on the inverter, and I'm going to show you some things that might help you teach this topic. So you could do this in front of your class. You could have them work together in groups, or you could have them work one-on-one as homework assignments. But we're going to go in here as a student, and we're going to go through a little bit of information here about the inverter, using interactive animations to kind of help bring this to life make it simple, because I think, this technology is so complicated that I don't know how we do this without using simulations in a way to break this down and make it simple. So we're going to start this thing up, and you can do this in front of your class. Here we got an inverter. I'm kind of jumping here kind of in the middle of this training. There's several preliminary lessons that maybe a student would go through before this. But for those of you who are not familiar with the Electude, we typically have some sort of some light text up here at the top that's important that the student must read. And then we have some questions or activities that kind of guide them through here. So the student would read this, or you might read this, read the few bullet points to your class, and then maybe even have them following along on their own laptops. There's several ways that you could do this. But you might ask them, what is the function of the inverter? So, here we got a multiple choice question. It controls the electric motor, right? So, and then we're going to go to the next question here. Where does the inverter get its energy from? Here again, you can ask your students these questions to have them answer this in class. It gets it from the HV battery, right? And so these first few questions, these are kind of introductory. For the interest of time, I'm going to jump ahead here just a little bit, and we're going to go to page 2, because we're going to learn, beyond just taking something apart, how useful some of these graphics can be in teaching this subject. So here we take it apart. Here's some electronics in there. Click on the cover to look inside. Okay, we did that. Click on the capacitors to look at the circuit board. Okay, we'll do that. The student might go, I don't know what the capacitors are. Maybe they click here first. No, that's actually the coil, but it doesn't have to always be cylindrical. So there's our electronics. Locate the signals of the inverter. Okay, so we got some different wires here. Here's the signal wires, and you can talk a little bit about the signal wires that would come in. Those are going to be covered here in just a bit. Click on the circuit board to take a closer look. Okay, okay, very good. We've got some circuits there, definitely. What are the electronics connected to? Okay, so if we look at this circuit board, what are they connected to? So this is kind of a discovery-based question here. The student may not know the answer to this, but there could be some clues up here in the text. And here it says, it's talking about these IGBTs. We haven't really discussed what those are yet, but they are connected to those. Click on one of the tracks that connect the circuit to the IGBT. All right, so let's click on one of those tracks. Okay. And now we come to a wiring diagram here. Now think about how much simpler this diagram is than the one we looked at previously. So let's study this here a little bit. I think these type of block diagrams, what they call it, are way more helpful to help kind of understand what's going on than looking at an actual wiring schematic for a component. So here we see the HV battery. It sends a state of charge to the hybrid ECU. It also communicates back and forth with the inverter. We then have our hybrid ECU here that sends a torque demand to the inverter, and then the inverter sends torque delivered back to the ECU. This is kind of an interesting part here, because here we see DC coming in, and then here's our AC, 3-phase AC going out to the electric motor. And we mentioned earlier starting with what we know, and if you think about a wiring schematic that's showing like a resistor, that you see an arrow that goes through it kind of diagonal like that, and what that means. Well, if this is AC but you see an arrow going through it diagonally, what does that mean? Well, that means it's variable, just like a variable resistor that has that arrow. So we have a fixed DC voltage coming into the inverter but the inverter is able to put a variable AC voltage to this motor based on the torque demand and what the driver is wanting to do there. So where does the inverter get its information from concerning the torque demand? The hybrid ECU, correct? Very good. What does the inverter do with the demand torque data? What does the inverter do with that? Transforms it to a signal for the HV battery? Transformed to a signal for the driver? Not so much. Transformed to a signal to power the electronics, the IGBTs. So that looks like the correct answer there. Which information does the inverter send back to the hybrid ECU? So we look here at the wiring diagram. The torque delivered to the electric motor, absolutely. The position of the accelerator pedal. What information does the inverter? Well, the inverter wouldn't have that information. The amount of energy, the state of charge of the battery. Well, I don't think so. I think the battery can probably send that information on its own to the hybrid ECU. But here again, this is less interactive because this is a recording. But if you can visualize maybe using this in front of your class and having a discussion about each of these answer choices, I think this makes teaching this subject much easier. You might go through 2 or 3 pages of this lesson together in front of the class, and maybe you break off into small groups and you have them, okay, so I want you to do page 3 here, now working on your own. So, and then you're walking around the classroom, you're looking over shoulders, students are asking questions. I think this is a much more effective way to learn than maybe just the teacher in front of the class giving a PowerPoint presentation or something like that. Because the students are actively engaged, they're answering questions. Either you're feeding them the questions, or they're reading them for their own and working on their own computers. But you're more of the facilitator of the knowledge versus the one who has all the answers here. So click on the circuit board. Okay, we're going to take a look at the circuit board. Here's those IGBTs, and here it kind of gives a little bit of explanation up here what those are. But basically they're heavy duty transistors, and it's these IGBTs that do the switching, the DC to AC, and also the AC back to DC when we're in regenerative braking mode. Click on one of the IGBTs, take a closer look. So we can click on this and take a closer look. Now, could we do this in the classroom on a real inverter? Absolutely. But could we do it as quickly and efficiently as we can inside a software? No, it might take you an hour to strip down that inverter to where you could actually see these. So plus making it really big on the screen, we can we get right to the point here. And some of these graphics too are simplified a little bit, because here again we're trying to get the point across to the students. So how many IGBTs does this inverter have? So they can do some counting here. So 2, 4, 6, 8, 10, 12, 13, 14. Yeah, looks like we've got 16 there all together. Okay, so this part is used for frequency control, or we'll probably talk about that here in a little later on in this lesson. But how many IGBTs are there for the motor? So it looks like there are 12 of these for the motor. Very good. Okay. What can an IGBT compared to? Okay, so here again, you could ask your students this question: What can we compare this to? This is a electronically controlled switch. Here again, no moving parts, all electronic. And here we have here again a close-up of that IGBT. Here's the wiring schematic for it, and so it looks like we got some diodes in there. Here's our familiar looking transistor symbol. An IGBT is a special type of transistor. What are the advantages of this transistor? Well, here again, so the student can read this text up here. It can handle a lot of resistance. I don't know about resistance, maybe current, right? It can handle large currents, indeed. Can switch quickly, yes, indeed. In fact, those transistors are switching thousands of times per second in many cases. So a lot going on inside that inverter, although there's no moving parts. Which terminal does the IGBT have? All right, so we can look here at the letters, and here again, I think this particular page here is probably would be good for students to kind of do this on their own a little bit. But this thing's got a base, it's got a collector. Does it have an emitter? Yes, it has an emitter and a gate. It's got all those things, doesn't it? Oh, what doesn't we have here? Looks like we don't have a. I guess don't have a base in an IGBT, do we? Okay. And let's skip ahead here just a little bit. This is the animation here that I want to show. So let's talk about how this inverter works a little bit here by using this animation. And I can recall a training that I went to years and years ago. There was a very, very brilliant man that was up there talking about how an inverter works, and he basically drew this diagram out on the board, but it took some time for him to draw that, and then it was a little bit difficult to follow as he was talking. But here again, with the aid of these animations, I think we can make this much simpler for students to understand. So here we see 4 switches, okay? And think of this here as one coil on that electric motor. And we need to make that electricity flow to the right through this coil. So here we got our battery. And you might even call, maybe this would be a good one here to throw up on the whiteboard and have a student come up in front of the class and say, hey, manipulate these switches and make the current go to the right. So, okay, well, we need to turn on this switch, and then we need to, which one of these switches here are we going to close? What if we close this one, what's going to happen? Well, if we close that one, that's going to create a short circuit. We won't do that one. And if we close this one, that ain't going to do any good because it's just on the positive side of the battery. We must close this switch here, and we send electricity to the right. Now we're going to change the diagram here a little bit, and we're going to put some transistors in there. So they don't necessarily look like switches because there's no moving parts in IGBT, but make the current go to the left. So now we got to make it go the other way. So what are we going to do here? We need to send electricity through this way and then ground it through this switch here. And we can make the electricity go the other way. So as students are going through this lesson, things are going to get a little bit more difficult as they go. So here, the next one, okay. Now we've got added another switch here because we've got 3 windings inside that electric motor, and this is where you, the teacher, can kind of add a little bit to this lesson here with your students. And you can talk about, the symbols on a 3-phase motor, your U, your W, and your V connection. And in order to make that rotor spin, we've got to change the magnetic field around the stator. So this would be your stator windings. And we got to make this magnetic field rotate in conjunction with the rotor. And the faster that we switch these fields on and off, or we make this magnetic field rotate, the faster we can make the rotor spin. So, okay, so what's it wanting us to do here? Make the red tip of the compass needle point straight down. All right, so I need to turn on some windings here to make a magnetic field to push this rotor around. So let's start with this one here, U. Let's put some power to that thing, and let's ground this one here and see what happens. Okay, so that moved it about 3/4 of the way around. We need to pull it a little bit more, so we're gonna switch this one here. Hey, there we go. We got it all the way down. So we turned on one up here at the top and two down there at the bottom, and that made that rotor spin halfway around. What do we got here on the next page? Okay, see, it's getting more. It's getting. We got a little bit more involved here now. Here we got. We're going to see all three phases moving here, and you're going to see the switches move. So I can drag this and see how this switch works. And here again, you can talk about this with your students and say, this is happening many thousands of times per second, that those switches are switching back and forth to make that rotor spin. And here again, they're doing it with no moving parts. Although you see these switches here, a transistor has no moving parts. Quite a marvel, isn't it? So as we go through here, we can hit the play, and we're answering some questions here as we go. What do you notice about the compass needle? Okay, so if we look at that compass needle there, it's not very smooth running there, is it? It's kind of erratic. It jumps around a little bit, doesn't it? And on the next slide here, it says increase the frequency. So if we speed this process up here, we can see how that rotor moves faster, but it's very, very jerky. And I think we all agree that would not be a very good driving experience. Be similar to driving a car on a washboardy road. It would not be a very smooth ride. But as you know, electric vehicles are extraordinarily smooth. Almost like riding in a roller coaster. It's so smooth, isn't it? So could we make this, smooth this out to where that rotor would spin more smoothly? Well, next slide here, if we could feed it with an analog voltage where we could gradually raise and lower the strength of the magnetic field going in and out of those coils, this rotor would spin extremely smooth across in its rotation. But can a switch do this? A switch can only be on or off, can it? So how does an electric vehicle operate so smoothly if I can't send an analog signal through these field windings? Well, let's see how an electric car does it here. So why is it impossible for IGBT to generate a sinusoidal voltage? Well, because it's a switch. We just talked about that. It can only be on or off, right? So how do we make this smooth? Click on one of the signals to have a closer look. So here's the signals coming in to these switches right here. You can see they're phased from each other. So we click on it. And let's take a look at this signal coming in. This is what is being used to trigger those IGBTs. And it's here again, if we start with what we know, think of like a signal going to a fuel injector. Here we have, these are various pulse widths. So we start off here with a very short pulse width. It's off for longer than it's on. Then it's on a little bit more, on a little bit more, and then it reduces, and this one looks just like the first one. And then it kind of repeats itself. So essentially what's going on here is we are creating a digital sine wave. So when we just barely turn it on, the magnetic field goes up just a little bit, and then we then turn it on a little bit more, and the magnetic field rises a little bit more, and we turn it on a little bit more. So we can make that magnetic field very smooth through pulse width modulating the current going through those stator windings. So we're basically essentially creating a square wave, a sine wave. And this would be a very difficult thing to try to draw on a board, wouldn't you agree? Well, so this is where I think having an interactive animation where you can put this in front of your class, and then you facilitate and you add extra bits and pieces to kind of fill in the blanks. I think this is a great way for students to learn. And you think about, we've been in here maybe 30 minutes talking about this, and we're changing the frequency, we're changing the percentage of on time. You can have these discussions with your students and increase your classroom efficiency. Here we got a little dyno. We can run the car on the dyno, and we can see as we speed up, we change the frequency of that pattern, and there's our sine wave basically to make that motor turn. So you might have your students go through some more of this, maybe page 5 here. You might have the students work independently or as a group, but now we're going to talk about the variable voltage side of that inverter. So we're going to talk about the step-up booster. And here again, we're going to use some technology. What do we know about a conventional car? Think about the ignition coil on a internal combustion engine, the ignition system. We have a primary and a secondary coil, the principles of induction. All that knowledge transfers over into understanding how this booster circuit works. So here again is many different relationships I think that you can make to relate it back to something the student already knows about the car is going to be key in helping them to understand how these things work. So here again, we don't necessarily have to answer all these questions here, but I'm going to jump here ahead to a point here where we want to talk about right here. So sometimes students ask, well, I'll never use Ohm's law. Well, sometimes I think Ohm's law kind of helps you understand helps you understand relationships and things like that, because with an internal combustion engine we talk about horsepower and things like that, but with electric motor we talk about watts and kilowatts and things like that. And watts obviously is measurement of power. And so here's a little simple Ohm's law question. We got a 6-volt battery. We got 500 milliamps, which is basically a half an amp of current. So how much power is this lamp going to consume? 6 volts, half an amp, 6 times 3. 6 times 0.5 is should be 3 watts, correct? All right, we're doing well here today. So if we increase the voltage and we keep the current the same, what's going to happen to power? So still a half an amp, but we increase the voltage. Well, we're gonna get more watts out of that, and so we can increase the power going to an electric motor by increasing the voltage, and the current stays the same. So we don't need any larger wires or anything like that, but we can make this motor do more work, have more torque by upping the voltage. So that power booster that we see here, that's basically what it's there for. It's going to take that, let's say 200 volts from the DC battery, and we're going to step up that voltage to this transformer to give the electric motor more power. And you could put your little grunts in there and everything and have fun with that, more power, right? So we're going to jump here just ahead here a little bit. I wanted to get to this diagram here. Here again, this is a neat little diagram because this shows our coil, and if we put power to that coil, the voltage here goes to 0 because we're dropping this 12 volts right now across this winding. So we're powering that thing up, similar to charging an ignition coil. And we know that when we take this power, open up this circuit, what's going to happen? Well, that voltage that that magnetic field that's around this coil right now is going to collapse over the winding itself, and we should see an induced voltage there in across this switch here when that happens. So when we charge the coil up, we take the charge off, and you see how we're increasing the voltage there, almost 60 volts. So we're taking 12 volts and we're turning that into 60 volts for just a short amount of time there. So yeah, we got a 12 volt supply, and find the coil. Very good. Close the switch. Yeah, we did all that already, didn't we? This would be a lot more fun if we were all together and when you get you guys talking. When you open up the switch, yeah, we did that there, and we got 60 volts. But if those of you that are maybe have Electude or have seen Electude before, this is a great way to train your students. We could even put this into a presentation mode. For example, if I wanted to talk about this, I can put it in presentation mode and just have the animation on the screen here without the words. That's a nice feature of the platform, because they realize that teachers will want to use these lessons to lecture from versus a static type PowerPoint. It would be a very difficult thing to draw on the screen on a whiteboard or something like that. So what we're going to do here now is we put a capacitor in between this in parallel with this switch. So here's our output voltage, and when we charge this coil now, when we turn off the switch, this capacitor is going to kind of soak some of that up. We're not going to get a huge voltage spike across these two terminals. It's going to gradually dissipate as that capacitor discharges. So here again, we want to deliver a very smooth power flow to that motor. So we don't want to send any huge spikes or anything like that to those stator windings. We want to send a nice smooth voltage there. So this is schematic. Take a closer look. What is the source voltage? And we got 300 volts here. Close the switch. What is the voltage across the output? That should be our output here. When we close this switch, here's our zero line. Of course, it goes to zero because all that voltage right now is being consumed to generate that magnetic field here inside that stator winding. Open the switch. What is the maximum voltage at the output? Okay, so we got 300 volts going in. Turn this off, and it goes to about right here. We're 100 volts per division, so that's 100, 200, 300, 400, 500. Let me do that again, make sure which line we're at there. Right here, that's around 550 volts, I believe. Alright, okay, so why is the voltage immediately zero when you close the switch? Okay, so when we close this switch, why does it go to zero? Well, because there we go. The induced energy is shorted through switch S1, okay. Alright, now we're going to add a diode in here. Okay, so that's going to, what was that diode going to do for us? A diode and a resistor are added in the electrical schematic. Open and close the switch again. Is the induced voltage shorted? Okay. So there it goes, kind of dissipates, doesn't it? It builds and builds off. I shut it down. It builds back up. Definitely it's not shorted, is it? Stays up there. Doesn't drop to zero. decreases very slowly. The diode blocks the energy that is shorted in the capacitor. Okay. And this resistor here basically bleeds that energy off very slowly when the motor's not connected. Open and close the switch again. Why does the output voltage drop? So I think this is another nice example where the students can watch an animation over and over again and see how when the switch opens, the voltage slowly degrades over time. We charge the coil again, but why does the output voltage drop? The diode no longer blows. The resistor causes the capacitor to lose energy very slowly. There we go. But now let's look at here. This open and close the switch again. Okay. I'm going to jump ahead here just a bit. I want to get to this point here where we move it very quickly. There we go. Increase the switch time. So if we increase this over time, we can get a very stable voltage because that capacitor is in there as kind of buffers this, even though it varies a little bit with the opening and closing of this switch. We've essentially got a relatively consistent voltage that's well above 300 volts through rapidly switching this switch. And this is essentially how that booster works, is by rapidly switching. We can increase or decrease that voltage based on how fast we manipulate that switch, or make it more stable. I don't know how you would teach this without an animation. I just don't know how you do it. So here we got more of a realistic schematic here now. This what is used instead of a switch? Well, there's our IGBTs. What is the function of the top IGBT? So here's our top one, here's the bottom one. Here we might have to read a little bit in the text here. So one of these is going to be to send electricity to the motor, and the other is going to be for regenerative braking. So the top one comes, the top one comes conducted during regenerative braking. Okay. And I know we're kind of running out of time here, but the main point that I wish to make about teaching this technology here is, I don't want to necessarily just go through the lesson piece by piece here. I mean, you can do that on your own, but through these activities here, we can go through the whole process. So we're going to start out here with the lower voltage, and that would be here at the DC battery, and that's our first step there. And then that voltage gets stepped up inside the inverter to a higher voltage, and then it gets digitized. And then through this pulsing, basically what's then sent to the motor is although it is a digital, it's a near analog type signal. So here we're seeing the whole process of what's going on inside that inverter. We're taking DC voltage, 300 volts, we're stepping it up through the use of those IGBTs, we're pulse width modulating those IGBTs to basically produce an artificial sine wave to make that motor run as smoothly as possible. And so after going through this lesson, although we did it rather quickly, it's about an hour and a half lesson if we went about it the right way. But I didn't want to necessarily just do that in this recording. By the way, it is very difficult to teach a class when you're not in front of a live group. I tell you what, I probably restarted this recording about a dozen times here this afternoon, but let's start this thing back up here and finish this slideshow. So here's kind of where we were before the lesson, and then what you might do with your students then is throw up another mind map after either you've gone through that lesson in class, or maybe it was a homework assignment. Maybe you assign that entire lesson as homework, and now you ask the students to basically do the same thing here again. What did you learn after going through that lesson? So maybe they add to what they know before. They might put three phase on the inverter, definitely IGDPs. You could put they would probably say, well, it steps up the voltage, but it also pulse width modulates the voltage and to make it really smooth. They might put a dozen things or more there up on the board. And sometimes what I find is interesting is it's not always what the students put on the mind map. It's what they don't put up on there that gives you, the teacher, a clue as to maybe what they didn't get in the presentation. So, like if nobody mentioned in class anything about the pulse width modulating of that signal, well, that might be something that you'd want to touch on then. Maybe pull that lesson open again, go over that point with your students. But there's a lot of ways that you can use these mind maps, I think. Maybe even as a test or something like that. And then there's variations of these mind maps that you can use, where you might put the topic there in the center, and they can come up to the board and write things up on the board. There's all different types of mind maps. I've seen clouds and things like that. One of my favorites is called a fishbone, which is where you put the topic here in the head of the fish, and then you write things that relate to that topic on each of these bones. But it's just an interesting way to do basically essentially the same thing we were doing here. But research these. I think it's a great tool to use in the classroom to gauge what the students know, or after you give a lecture or after they go through a lesson, what they retained, and then it gives you like a springboard, something that you can then use to expound upon. So I hope that this hour or so discussion, although largely just me going through a lesson, was at least helpful and maybe make you think about maybe some different ways how you might be able to teach this technology. Really, the whole point that I was trying to make here is we, as trainers, we can't just continue to do things the way we've always done in the past. Because this technology is so different, it's abstract. You can't see parts moving like you could on an internal combustion engine. We have to change the way we teach this, because if we don't, if we just if we overcomplicate things or make that inverter seem like some kind of magic box that no one can figure out, students may not choose this career field because they don't feel confident in their knowledge of how those things work. But if we can break it down, make it simple through the use of animations, through maybe changing our lecture the way we do lectures and things like that, we can make this technology seem simpler, and students will have the confidence to go out there and do it. So really, that's the gist of my presentation. Here's another mind map that you might use. So typically I would open this up to questions at the moment, but because this is a virtual presentation and it's actually a recording, I guess I will say farewell and thank you for watching this to the end. Hope it was helpful.
Okay, that concludes another session of the Western Wheels Conference. A big thanks to our presenters. Don't forget to request your certificate if you need one, and we'll see you around next time.